All right, everyone, welcome back. I hope you had a good spring break, which means that you did more shifts at work. Oh, sorry, I know that's how it is, but still, a little bit of a refresher right after that last exam, and I know that last week was probably a little bit of a wash, and probably you haven't even watched those videos yet, so you might want to get caught up. So the good news is that this next third of the class after test 2 is way different. We are going to end this hydrogen atom, this and that, largely today. It shows back up a little bit, we're going to start talking about spectroscopy today, and I'll use the hydrogen atom as an example. But the point is that we're going to slowly more and more diverge from quantum this, hydrogen atom that, the further we go. At the end of this block of this last part of the course, we're going to end on kinetics, and kinetics has nothing to do with quantum. It is about differential equations, but they're actually way easier. As I mentioned to you, a lot of faculty start the class with kinetics because they want to start easy, but I end on kinetics because I know that you got, at this point, you probably got a lot going on with other classes, graduations coming up. What are you going to do next? So I'm going to actually try to de-stress the situation by giving you the easiest part last instead of first. I hope that makes sense. I don't know. I have to make some kind of judgment. That's the one I made. Okay, regardless, we're not quite done with the hydrogen atom, this and that yet. We are going to finish it today in terms of wave functions. Let me remind you what we talked about the last lecture that you still haven't. Oh no, you would have watched it by now, right? You're hopefully watching these in order. You probably just watched it an hour ago as opposed to a week ago. That's fine, as long as I hope you just keep up, not just before the exam, because that's crazy. That doesn't make sense. All right, separability. You know how much I like separability. I'm sure that'll be on the final. The wave function for the hydrogen atom with this ultra complex Hamiltonian. Remember those lectures went across the board twice. Separability says that the wave functions are one of r, theta, and phi. The radial ends up being the most important. It's the primary Schrodinger equation of the many Schrodinger equations. The radial ends up being the most important for whatever reason. I don't really know. It just is. The energy, E, the eigenvalue, funnels into that one. So there you go. So it ends up being really important. And we solve for the radial wave function, and remember that it has, a lot of the rigmarole that we went through was to show that it has an r to the L component, some other stuff, and e to the minus r at the tail end. So here's the front end, here's the tail end. And we see that in the graphs. Remember, I'm still just reviewing. We see that in the graphs of the wave function versus r. And here's what you can expect on, I don't know if I have these on your homeworks, but I will have it on the third test and the final, is identify what's what. Now you should be able, I guess this is a little bit of a, what do you remember question. I don't like those, but what else am I going to do? And maybe I'll show, I'll throw that up at you and say, hey, what's what? The answer is that this is clearly a 1s. That is a 1s radial wave function. And how do I know that? Because r to the 0 is a constant. So at an r of 0, the wave function is finite. Now remember, that's some math speak. When I say something is finite, it means not 0. And this, whatever this is not 0. Now the other thing I know, so I know it's an S state, but I also know it's a 1s state because there's no nodes, right? It does not cross 0. Now this next one I've drawn is also finite at the origin, so that makes it an S state, and it has one node. And so clearly that is a 2s state, right? That's an excited state of hydrogen. Hydrogen is probably predominantly in its 1s ground state, but it can be excited by light, and which is going to be the subject of the next week, spectroscopy. It can find its way into a 2s state somehow. Now I'm saying that because, I'll put this on the exam. I always get burned up when people say hydrogen's in the 1s state and the other states don't exist. They exist, they're just excited states. So anyway, I said that a couple of times now. Okay, next one. Okay, what's that one? All right, well, for various reasons, it's actually a little tricky, but I know it's not an S state because at R of 0, the wave function is 0. Now that means that, so what I'm seeing is an R to the L, where L is not 0. So this is like an R or R squared. Now, if it's R to the 1, that means it's a P state, right? So this looks to me like a P state. Again, mostly because at 0, the wave function is 0. Now, there's also no nodes. So that means it's likely a 2P state. Now, it could be X, Y, or Z. I don't know that. Those are the angle parts. You can't know that. But it definitely is a radial 2P. So there you go. Now, let me point out, I don't think I'll put this on the test, but I want to point out that it actually would be quite difficult to know the difference between a 2P and a 3D. Now, a 3D would not have nodes, a 2P does not have nodes. So how would you know the difference? The answer is it's actually really tricky. It's really hard. If you put those two graphs next to each other, they would appear almost identical. Let me point out actually how they're different. Notice that a 2P scales as R, but a 3D would scale as R squared. So what that means is, at the origin, a 2P kind of looks like that, and it goes on, versus a 3D looks more like that before it goes on and on. Right, you see R squared, this is like y equals x, and this is like y equals x squared. That's how you would distinguish. But for the most part, they would appear the same. Now, you may notice I'm going down a rabbit hole of really fine minutia. Yeah, so let's not talk about it any further. I just wanted to point it out that it's just, there it is. So that's how they're different. Okay, I'm still reviewing, and I don't really want to review anymore. So what we're here to talk about is actually we're going to go back to the angle parts, which you thought were done. You hopefully thought they were done because we mostly finished talking about those, or we ostensibly finished talking about those when we were doing the 3D rigid rotor. So remember the thing that, the logic that we follow in terms of how I and everyone else who ever taught this class, the logical flow is to do 2D rigid rotor, 3D rigid rotor, and hydrogen. Now the reason that is that the 3D rigid rotor is part of the solution to the hydrogen atom. The hydrogen atom diverges from the 3D rigid rotor in that it's not rigid, right? The radius can change. The electron can approach the nucleus. It's not on a string. That means that you get a radial miniature Schrodinger equation, which is really important. So the electron can approach the nucleus, and we've talked at length about that. That's where the energy comes from. It also has a Coulomb operator, right? So regardless, these angle bits, though, these angle bits are the 3D rigid rotor wave functions, the spherical harmonics. There is actually still a little bit more to say. And this, again, this part's kind of easy, and it's going to be a little important when we get into spectroscopy, so that's why I'm kind of circling back to this. Hopefully it'll make a little bit more sense as I just start rambling on. Okay, what do I want to say about this? So we're going to talk about, we're not going to talk about S states. Remember that the wave functions for the angles are just constants. It's just a normalization constant for the S states, 1s, 2s, 3s, on and on. There's nothing to talk about. Remember, it's not rotating, which is so weird because it's round. Regardless, let's talk about L equals 1. Let's talk about 2p and 3p and 4p states. And I guess there's 5p. Now remember, if you go n too far down, you run out of elements. Elements can't get so heavy for reasons we talked about before, because the electron will crash into the nucleus. So here we're talking about the p states. Okay, now there's a wave function for those, which is going to depend on theta and phi. I've already established that L, we're going to talk about p states, so L is 1. So the only other thing to talk about is the m state, where m is dictated by L, which can be either -1, 0, or +1. I've written them in this order because, again, so we look at the solutions from a literally 16th century textbook, and the 0 is cosine, the positive, right? So then the things are sine with e to the I phi, and then sine e to the minus I phi. Oh, that doesn't look like a good theta, it bothers me. Okay, so there you go. Those are the solutions. Again, we've already covered these. Now, here is something, as today's lecture, I'm going to just talk about one subject, and I hope it actually seems familiar. What I'm going to talk about today, I've actually already covered it, little bits and pieces throughout previous lectures and homeworks. Everything I'm going to talk about, I've already covered. And I've done that to make all this as easy as possible, plus it's the first Monday after spring break. What I'm going to talk about is actually how these two are weird. They're weird because this is real, and these two are imaginary. Now, what I mean by that is that I have an e to the I phi and e to the minus I phi. And there's no I something something here. So fully real, and these have imaginary components. So that's a little funky. How do we tell high school and freshman chemistry people about this? Right? How do we explain that? Well, you may recall that we explain all this by px, py, and pz. And again, some of you are probably recalling, I've already dropped this information before, but I'm going to formally introduce it, and I hope it's easy because you have seen this before. And what I think I've already shown you is that this is the pz orbital, but neither of these are px and py. And let's see here. I should be showing, if I recall to do this correctly, I should be showing the wave function for L1, M0 here. And you can see that it looks just like a pz state. But when I show you L1, M plus 1 and L1, M minus 1, those don't look like px or py states. So that's a hint that there's something not quite right here. Okay, now, I haven't done this part yet, so I gotta remember to do it. I'm gonna show another little video here. These are traveling waves. Now, a traveling wave is what you see here. It's a wave that I'm showing just a series of images of a wave, but of course, the representation over time makes it look like it's moving along. I'm riding a horse. Oh, don't tell anyone I said that. But so it looks like it's a traveling wave, right? And that's an e to the I phi or an e to the minus I phi. Now we're used to these as being like free waves, and we know that they travel along, all right? But that's kind of funky for what we think of as like a stationary state. Remember that extra lecture I gave about hydrogen atoms, about how in their ground state, or even an excited state, the states, if they're not superposition states, they don't evolve in time. Yet this wave is moving along. All right, now let me contrast this with a standing wave. Now you can see that here. You can imagine what that is. If you get a string, by the way, I should have brought a string. I should have just done this in person. But if you get a string and it's attached to a wall, and if you move it just right, you can make a traveling wave. But when you get the frequency just right, you get this example here, which is a standing wave. Now, this standing wave is more appealing to me from a quantum mechanical principle, because I think of this as something that's not really evolving in time. And again, maybe you didn't watch that extra lecture that I had where I talked about the time-dependent Schrödinger equation. You don't have to. It's an extra lecture. It's kind of a graduate school thing. But I did show you if you were interested. And again, this standing wave is way more appealing to me for a solution to the Schrödinger equation than that traveling wave. Okay, so it turns out that I can get the traveling wave to look like a standing wave by making a linear combination. Okay, now you may recall that, okay, so that's gone, that at one point I had you do the flux And I think I used an e to the I phi representation, and the answer was 1 over r. Now, I'm not quite sure how to interpret that necessarily. I know it's not 0. I'm looking for a 0 solution. This is not 0, and this means that the thing is moving. It's the traveling wave like you just saw. But now the flux, now remember you had this on a homework, the flux of a linear combination plus or minus. Now again, on your homework before, homework 7, that was 0. The flux of that is 0. Standing wave. It's a standing wave. Besides, look at that. You know what that is? That's sorry, my handwriting is really bad today. I've actually not been digging this in a while. You know what that is? It's 2 cos phi, right? Standing wave. It also doesn't have an imaginary component. Now remember, I'm also motivated by showing freshmen and high school students what this stuff is, and this is a nightmare, whereas this is junior year high school trigonometry, right? So this is much more appealing. So what I'm seeing here is that I'm going to need to make linear this guy's cool, but these aren't. What I'm going to do is I'm going to make linear combinations of these two, and that's where my px and py orbitals come from. So I'm going to do that, but last bit before I just start writing stuff down, and I'll have some nice graphs here and there. And I'll probably put this on a test, so ears perk up a bit. This is the crazy thing that I still have a hard time with. These are perfectly fine. Seriously, there's nothing really wrong with them. They are solutions to the Schrodinger equation of the Hamiltonian of the hydrogen atom. They are totally fine. They give the right energies. I can use them to describe whatever, and I will get the right answer. However, for all the reasons I just mentioned, they're not appealing for all those reasons. So it's a funny thing, right? So I am making it harder. I'm going to make linear combinations of these, which is like, oh great, so that's a little bit more complicated. Correct, it is more complicated. However, once I do a little bit of little mathematical this and that, then they actually will get easier, and you can see a little bit more about why I do it the way I do it. Okay, anyway, just some blurb there. Okay, let me wipe out that part, and okay, so again, for stupid reasons, I have decided to make linear combinations of these spherical harmonics. So let us do, security guy came by. Okay, so sorry about that, security guy came by. Okay, so I'm going to make linear combinations. All right, so L equals 1, M equals plus, no, 1 is plus 1. And let's add, we'll subtract it later. Okay, so there we go. All right, now what does that turn into? I'm going to go ahead, for time's sake, and factor the sign. The sign is common to both. And I got e to the I phi plus e to the... You're probably wondering, why am I even writing this down? Because I just did this a second ago. You'll see, I actually have a little bit more to say. So remember that this is cosine. I just mentioned that a second ago. Now, 2 cosine, but you don't have to worry about constants. Those are eaten up by the normalization. So this is really 2 cosine phi, and I just wrote down cosine phi because the 2 doesn't matter. Imagine that you're solving these wave functions. Once you get them, remember you always have to normalize it after the fact. So little factors of 2, those don't matter to me. Okay, so there's that. All right, now let's do m equals 1 minus the same thing. Okay, so what does this do? Again, the sign factors, and you see that this is quite an easy problem, especially because of all the, I've been beating you up for a long time about e to the kx and e to the I phi and all that stuff. It's a sine function, right? So this is sine theta sine phi. Now I know that there's a factor of, this is technically 2I sine phi. Same deal. It just gets eaten up in the normalization. Even the fact that it's complex, even that doesn't matter. It's still a constant. The letter I is still a constant. It still gets eaten up in the normalization. Does not matter. So there you go. Sorry, I should put a little sort of. Okay, now what's actually the point of this? Now hopefully, given all the rigmarole I said earlier, I'm just kind of repeating myself. So what's the point of this? Recall, now I'm going to tie it together. Recall in spherical coordinates that z is our cos phi, x is r, everything is r something. R sine, cos theta, and y is r sine theta sine phi. Okay. So notice this. L of 1, m of 0 is a pz orbital, right? Because cos. See that? Now remember, I showed you this graph earlier, and hopefully that's showing it right now. Right? This one was always identifiable as a pz. Now these, again, I've shown you these already, they don't look like anything. Like nothing you've seen since high school, so what the hell? The answer is that if you add them together, sine cos, oh look at that. This is px. And I'm showing that here. I've got to remember to do that. That's what that looks like. That's a px. And what is this? Sine y. So that's py. And you're seeing that here. So that's where we get these from. Right? So not too mind-blowing, right? Okay, so I've got about 20 minutes left. Let's up the game, and we're going to do d orbitals. Same trick with d orbitals. Now I'm going to do one example. I'm going to show you one rule that's probably not apparent right now. There is a rule about how you combine these together. I will show you that. It's not apparent in this case because this is, to be blunt, very simple. When you get to the d orbitals, it gets a little bit more complicated. And on your homework and exam, I will ask a different question, or maybe I'll ask about an F orbital. But again, the trick will be evident once I talk about d orbitals. I'm going to just wipe out the board. The security guy has to be, that's why he came by earlier, he has to be let back in. So I'm going to wait for him to be let back in. And we're going to start there. And we're going to end with a little bit of an intro on spectroscopy. And anyway, I hope that this is kind of a soft return back to class. So give me one moment, I'll wipe out the board. Okay, everyone, so d orbitals. Here are all the 3D spherical harmonics for the L equals 2, right? Those are d orbitals. Of course, there are 5d orbitals. Remember, there's dz squared, x squared minus y squared, xy, yz, xz, I guess. I don't quite remember, but something like that. And now we know that we're going to need to make linear combinations of these things to tease that out, right? Remember, our goal is not to have not to have a traveling wave, which means that all these e to the I feeds and e to the minus I feeds, we actually want to get rid of them. So you saw the strategy we had with the p orbitals. We're just going to adopt that for the d orbitals, and then we're looking for to connect them back to what you learned in freshman chemistry about d orbitals. Now, of course, we should have 5. Now, recall that the allowed degeneracies are realized by the m quantum number. It's like the sub-quantum number, m sub l, and it goes from minus L to minus L plus 1, to plus L. Okay, so that means we're going to a minus 2, minus 1, 0, 1, 2. Okay, I know I wrote them in maybe a funky order. Notice that, I should be able to, let's look at a potential test question. I'm kind of going off on a tangent, but I just want to point out where I could ask a test question. Notice how by definition, remember the 2D rigid rotor, you see e to the im phi, e to the, in minus 1, e to the minus I phi, 2, minus 2. Okay, so you can imagine I could write down a d orbital, and I could at least ask you to identify the m quantum number. You know what I could do? I could just throw one of these at you and say, hey, tell me all about it. And you would say, okay, well, m is, let's look at this one, minus 2. M sub L is minus 2, right? We often call these M sub L. To remind you, it's like a sub-quantum number. So you could say, well, this is an M sub L of minus 2, and therefore I bet it's a L of 2, it's a D state. You would be able to tell that just because you recognize the quantum number there, and you could tell L from this little rule here. Now, it could be an F state, and if you were to say something like that on the test, I would give it full credit. But anyway, I just had to stop there for a second to point out a potential test question. And an easy one, right? That's actually kind of easy. All right, anyway, I've gone off on a tangent already. Let's see. Now, I told you that we're going to do one example, and on your homework, you're going to actually do the rest. I'm going to give you one d orbital, and then you're going to find the other 4. I'm going to give myself an easy one. Now, let's see here. It's all going to be combinations of these, because e to the I phi is a traveling wave and we don't want that. Okay, so why don't we do the M sub L of 2, and I'm going to pair that with minus 2. Now notice that you're never going to pair a 1 with a 2. You know, M sub L of 1 plus or minus an M sub L of 2. Do not do that. Now that's because you can't make the I phi thing, it can never go away. You have to combine a 2 with a 2 and a 1 with a 1. Okay. And I won't say anything further about that. Just remember that when you're doing your homework. Okay, so I'm going to do L of 2 by definition, M of 2 plus 2. Now I'm going to add the only thing that I can add, which is the minus 2. Remember, there's no other pairing that I could do with that. Now, what I also could have done is I could have subtracted them, and you're going to do that on your homework. And when you do that, you're going to identify a different D state. Okay, regardless, I look at this sucker here, and there's, of course, let's see here. Okay, so I can see that there is a sine squared. I'm going to factor that out. Sine theta squared. And then let's put the offending things, the imaginary functions. These are the things we want to get rid of. Okay, now hopefully you recall that this is like cosine. It's like 2 cosine 2 phi. Remember from homework 2 or 3 where I started, forcing more and more of these exponential, these imaginary identities? It's because of all the times you've seen them, including now. Now, hopefully, again, you recognize that as a cosine. Okay, cosine 2 phi. Okay, so now I've got this sine squared phi cos 2 phi. Now, one thing to recognize as well is that, again, like last time, I'm not worried about the factor of 2 because everything gets normalized. As you've seen so many times, I often construct the wave functions from my head or an 18th century math textbook, construct the wave functions, normalize it later. So that factor of 2, nothing to worry about. Okay, now, right now, I don't see anything I can work with in terms of trying to identify a D state. Remember, what I'm looking for is dx squared minus y squared, xz, yz, the other one. Okay, I don't have anything to work with here, but now what does it mean to have something to work with? Okay, it'll be smashingly clear at the end. It's just like the P state, it's just more complicated. And what I do on the homework is I give you the necessary identities. Okay, so for cosine 2 times whatever angle, and I just Google this, you can find a couple of identities. So that's one of the challenges, is to find the right one. So on the homework and on the exam, I'll give you the right identity. Because that way, you know, I don't want you wasting your time. It's not like, I don't consider it like cheating. Cos squared minus sine squared. There we go. Okay, again, there's a couple of identities, but of course I'm going to give you the one that gets you straight to the answer, because otherwise I'm just testing your time efficiency, and that's not that that's not useful, but okay, now I've got this. Okay, let me come over here. I'm not using the board super well, but let me come over here and looking at the answer. Okay, what I'm going to now do is distribute the phi squared cos squared minus, maybe I should have never distributed the sine phi squared. Okay, now recall what the transformations are from Cartesian to spherical. So notice that the d orbitals are written in terms of Cartesian. X squared minus y squared, xz, yz, and of course we're in theta and phi land. So to identify this one, we want to look back at our transformations, and of course what you recognize is sine cosine is x, so this is x squared, and of course sine is y, so that's squared is y squared. So this is d, sorry, that's a partial. It's the d orbital, x squared minus y squared. Okay. And you can, maybe I'm animating that above my head, and that's what the dx squared minus y squared looks like. Now I got to remember to do that. And there you go. Okay. Now, the last bit for your homework again is take this one and subtract them, and you'll get a different result. Look for the identities, which I give you again so that you're not completely wasting your time. Do that for these. Now again, this one is usually unique. The m sub 0 is usually rather unique, so you should be able to identify that one very quickly. And there you go. So, and last but not least, I just want to remind you, I know I've already said it, and I still find this so strange, that it's not like there's anything wrong with these answers. If you do quantum mechanical calculations like the ones we're about to do, and you keep these wave functions exactly as they are, there's nothing wrong. You will be able to still calculate observables and get the right observables. Now, you can make linear combinations and calculate observables and still get the right observables. Nothing really changes. All you get is the ability to write these things down without e to the I phi and confusing the living heck out of freshmen and high school seniors, right? You don't want to confuse the living heck out of them, and this is what this allows you to do. And I think there's a lot to be said for that. But the expense is now you come to my class, and now I have to unravel that and explain why we do it that way, even though it's unnecessary, right? So I don't see a letter I in there, and that's what it all comes down to. Silly, but that's how it works. Okay, now I do have 10 minutes left, so I want to go ahead and start in on a new subject, which is spectroscopy. And I do have to warn you, I know I said that we're largely done with writing wave functions out the wazoo. I actually do have a couple more that I do have. Sometimes I'm going to write equations across the board. So sorry, but it's not, I guarantee you, I know that sounds scary, but it's not nearly as hard. You'll see. I mean, we're going to start on this next class and the class after. We're definitely going to be writing some really long equations, but I guarantee you it's actually very easy. So, so what we're starting at now is spectroscopy. And what we're going to do is cover why things absorb light. Now we talked a little bit, I had that funny movie of it wasn't quite a harmonic oscillator, right? It was the Morse potential, which you had in PChem lab for the acetylene module. And so you know a little bit about this by now. By now all of you should have gone through your labs, I hope. And you saw how a wave function turns into another wave function with an application of an electric field. Now that was a vibrational transition. What we're going to do here is we're going to cover electronic transitions. Those are a bit more relevant, and I'm going to show you how we know whether a transition occurs. And I've got some cool videos. I think I'm going to show them next class. I'm going to show you hydrogen atom. Well, the hydrogen's electron, right? Hydrogen can't vibrate because it's just an atom, but the electron can undergo transitions. So I have videos of the electron in an electric field that's going up and down. That's a photon, and you can watch it transition from an S state to a P state. So I spent a long time on that. I hope you find that kind of fun. That's next time. And so that's an electronic type of transition. Electronic transitions are all in the visible UV X-ray. Right? Now, if I'm talking about lower energy, then those are vibrations. And if they're lower energy still, then those are rotations. We're going to cover that in more detail in about a week. So, spectroscopy of electronic absorptions. Again, these are relatively high energy. They're in the visible UV X-ray. Now, the reason that this is relevant for a biochem class is actually, now I think I told you this, I can finally get into some stuff that's more biochem relevant. I really wasn't able to before, and that wasn't because I didn't want to shortchange you. It's because it's been freaking talking about a hydrogen atom, right? Now that we are moving away from that, I can give you a lot more information I think you will find more useful. And I'm sorry I wasn't able to do that before, but it's just the nature of things. When it comes to visible spectroscopy, I'm going to tell you a little story why this is relevant for you. You people who, you want to be doctors, you want to work in the medical field, fine, we need people to do that. But you should know, all of you who volunteered in the hospital, you know why I'm doing this, right? What happens when you bring in a patient, no matter what, you bring in a patient, and the first thing they get is the clip on their thumb, which is the oxygen meter, right? Especially for COVID. And what it is a red light that goes through your thumb. And what it's doing is it's measuring the absorption of that red light. Red goes through your thumb pretty well, goes through skin. What stops it is hemoglobin, oxygenated hemoglobin. So what it's measuring is the absorption of red light by oxygenated hemoglobin. So if the red light shoots right through, you have no oxygen in your blood, and you're dead, all right? Around below 90%, you are in trouble. If you're at 80%, you need to be on a ventilator. And I think, I'm speaking out of my rear end, I think if you're in the 50%, you're going to die right there and there. They can't save you at that point. Something like that. I only know that because of the stuff going on. Okay, so that is an optical electronic absorption. So that's what I'm going to put everything in context. I'm going to specifically do all of the mathematics with the hydrogen atom because that's as easy as it could ever humanly get. And from this, what we're going to learn, the goal is entirely this. Now, there's all kinds of things you could imagine. There's so many parameters to optical spectroscopy, and we could try to solve all of them, whatever they do and how they do it. We're going to focus on one simple thing. It's real simple. Absorb or not. Does this thing absorb light or does it not? From that, if it does absorb light, we'll know what wavelength of light it is, and we can translate that to either being red, blue, or green and whatnot. So this is really all we're concerned about. If you know something absorbs, then the wavelength that it absorbs is simply dictated by the difference in energy from the initial to final state. The initial state will usually be the ground state because most things are in their electronic ground state. Now for us, that means hydrogen is in the 1s state. Anyway, I'm getting a little ahead of myself. I think that all makes sense. Okay. Now, in terms of details, we're going to have to write integrals across the board, but integrals of what? Well, we got to know what we're talking about first. And what we think of is that, especially for electronic visible UV-vis spectroscopy, we always say that these are dipolar transitions. And that's like 99% of what goes on. So we're just going to leave it at that. Okay, so a dipole, of course, is when, think back to your physics 2, right? E and M. Usually, sorry, that Q, that's a bad looking Q, isn't it? Okay, we typically would think as having a plus charge and then a minus of that same charge. Most things that are dipolar would look like that, because if it wasn't the same charge but different sign, they would have a net charge, which is kind of unusual. Most things aren't floating around in the air or your blood with a net charge. That's rare. It's rare because those things can exist, of course, but they're unstable. They would react with oxygen. So, for the most part, we think of things as being polar, but having the same charge, so that it does not have a net charge. Now, the dipole moment, and again, it's okay if you don't recall your Phys 2. So there's a distance between these, let's call that distance d, and so that gives a dipole moment of q dot d, and I need to put that as a vector for reasons you'll see in a moment. So the distance matters. The further separated, the greater the charge, the greater the dipole. And it matters what direction it's going in, and that will become smashingly clear in a moment. So you might recall things like field lines. So again, maybe I should be computer drawing this, but yeah, so there's field lines, and anyway, just think back to Phys 2. I barely remember it myself, and I kind of do this stuff for a living. Okay, now what is important about, no, that's awful, sorry. What happens is in an electric field, the dipole experiences a torque, right? So it just twists it, wants to give it a twirl. Unless, of course, the electric field is aligned with the dipole, in which case it doesn't turn at all. It would maybe be lower in energy, but again, if the electric field is lined up with the dipole, then nothing would happen, and that's why you need to consider the dipole as a vector, and all the complication that comes along with that, although it won't be too bad. Okay, now that's actually not important to this. I just want to remind you a little bit about how E and M works. Let's see, the last bit I want to cover, and I see I'm out of time, is just this. Change in E is, which gives us the wavelength of light, right? So H frequency of light, of course, is something you look up as being visible or UV or X-ray or whatnot, is simply the excited state energy minus the ground state. Again, we'll just assume that everything's in the ground state. We're going to work with hydrogen, so hydrogen's always in the 1s state. Now, go back to absorb or not. So you see how this game works? Is I can always start with the 1s state of hydrogen, and then I can query every excited state. Now that includes 2s, 2p, x, y, and z, and I might need to think about x, y, and z because of the way that this is a vector. I can think about 3s, 3p, 3d, 4s, 4p, 4d, 4f, on and on and on. Now what I'll do is the quantum mechanical calculations on a 1s and all those excited states, and I'm looking for absorb or not. If it absorbs, then this energy difference corresponds to something that a spectrometer measures. So that's exactly how this game works. Now, last bit, I want to point out that in terms of why this is important, you can ask, let's say that hydrogen is in an excited state initially. Let's say that hydrogen is in a 2px state. Sure, why not? It's in a 2px state. Does it, and also I want to show you, this is how we write these transitions from right to left. It's a little weird, but it's a convention. Does a 2px absorb light into, say, a 2s state? Would that happen? Or maybe another 2py or 2pz state? The answer is no, because those are degenerate. They have the same energy. Okay, so the energy difference is 0. If I plug in 0 here, that's no frequency. No light has no frequency. So you can't get transitions in energy when there's no difference in energy. So that's just kind of maybe that's an early test question because it's kind of stupid. Anyway, all right, that's all I have for today, and I hope this is a little fun. We're going to get into the weeds in a big way next time, but I've got some really cool videos, so I hope you enjoy that, and I will see you all then.